Hello everybody, this is Raj trying to make up for the lecture that we missed. I'm going to go to the course website and download the slides just to make sure that I'm talking with respect to the latest slides. You'll see here that it's July 31, so this is what we're going to cover. And where are we? I'm going to go to presentation mode, and I'm going to go to this bit which about the dpll procedure, because that was what we missed. Okay, so what does dpll require? It requires a conjunctive normal form. So conjunctive normal form is a formula of this form. So the idea is that you have a row of literals, and each element of the row is separated by a disjunction, and then each row is conjoined with the other rows. Now, to convert the given formula f into an equivalent f prime, which is in C and F, what do? We first of all transform f into n and f. How did we do that? Well, remember that was use all of these rewrite rules from left to right. Okay. And then whenever we find something that breaks this conjunctive normal form, we use these rewrite rules. So why does this break the conjunctive normal form? Because the outermost connective is a disjunction, and the things inside it are not literals, right? So this is an OR with ands inside. We want ands with ORs inside. So we write it to this form. So now what have we got? We've got ands with ORs inside. Now if one of these broke it, so if one of these was a conjunction, we'd do the same again and keep going. Okay, so there is a way to convert any given formula F into C and F. And now we're going to look at the dpll algorithm, named after the 4 people who made the major contributions to it. So dpll deals with clause sets. So what is a clause? We already know. A clause is a disjunction of literals, and a literal is either an atom or a negated atom. We're going to say that a clause is a unit clause if it consists of exactly just one literal, right? So it's either an atom P or a negated atom, not P. That's a unit clause. Okay. Then what we're going to do is we're going to take a formula in C and N, F, such as this one, right? Conjunctions on the outside with disjunctions inside, and the things that are disjoined are literals, right? What we're going to do is we're going to take it as a set of the disjuncts. So we're going to drop these conjunctions, put set braces around here, so that now what we've got is a set of clauses. All right? Because remember, a clause is a disjunction of literals. So each one of these is a disjunction of literals, and we've got a finite set of them. Okay. Now, what are we going to do? What we're going to do is we want to know, or we're going to answer the question, whether some formulae, axiom 1 up to axiom n, implies the conjecture. Right? So what we want to know is whether for every interpretation, if the interpretation makes all of these guys true, it makes this true. Well, what that means is that the conjunction logically implies the conjecture is a valid formula, right? So we can replace this with the normal implication and demand that that formula is valid, right? Well, what that means is that that's the same as saying that the conjunction and the negated formula is unsatisfiable, right? You need to work through that. So this is, the implication formula is valid if and only if this is unsatisfiable. So both dpll and resolution look at trying to determine whether a given set of clauses is unsatisfiable. Now the way it does this is that it does it in a bottom-up way. So what we saw with the tableau method, for example, was that you're given a big formula and you break it down according to some rules. Here, what we're going to do is the opposite. We're going to start off with the big formula, but instead of breaking it down, we're going to look at the atoms that make that comprise the big formula, and we're going to go through the truth assignments for them one at a time. And the way to organize this procedure is to do it using something called semantic trees. So what we're going to say is that a rooted tree is, the normal thing. It's got a root and it's branches, it's got children. We'll always deal with either a binary, every node will be binary or unary, so we won't have to worry about anything more. And we'll say that a branch is consistent if you never find a node containing A and a node containing not A on it. Right? So the nodes are going to be literals, and a branch is going to be consistent if you never find an A and a not A, right? Because then it would be a contradictory. So the intuition is that you're going to make all the things on the branch true, and you don't want to make both A and not A true, right? Because that's inconsistent. Then every branch is going to be taken as a model. So what we're going to do is we're going to say if the literal A is in S, then the model A maps, the interpretation maps A to true. If not A is in S, then the interpretation maps A to false. And if A is not in S, and not A is not in S, in other words, S doesn't mention A in either of its form, then the interpretation is going to map A to false. Right? So the things that are not mentioned are implicitly going to be false. Right? That'll become true later on. That'll become important later on. Okay. So for example, if this is the set S, then it stands for A maps to true, B maps to false, D maps to true, but because C isn't mentioned, then C maps to false. Okay, and what we're going to do is we're going to say that a model for a clause set N is just an interpretation that makes every member of N true, right? So remember, it's a set, so it has to make every one of these guys true. Why? Because implicitly, the comma is a conjunction, right? So you want to make this true, and this true, and this true, and this true. Okay, so let's go on. So here is how you do dpll using a semantic tree. I haven't told you what dpll is at the moment, so I'm going to just go through the intuitions of building a semantic tree. So currently we have the empty tree. So what does that mean? That means that every atomic formula is mapped to false. So here's everything mapped to false, and we start with the first clause. And, well, that thing is going to make A or B false, because A is false and B is false, and therefore this is false. So what can we do? Well, what we can do is we can do a branch, left branch which makes A true, and a right branch which makes A false. So here it is, right? So this is a decision. So what we've decided is that we're going to explore the two truth values of the literal A. So A is true or A is false. All right, well, what does that do? Well, what that means is that now this guy is true. If we look at the left branch, this guy is true, so we move to the next guy. Now, this A means that if A is true, then this is false. So that means that in order to make this guy true, we have to make C true, right? So A by itself is making C false, right? Remember, if it's not mentioned, it's false. So A true is making this false, and it's making C false. Well, what we have to do now is change the value of C, the implicit value of C, from false to true. So what we'll do is this. We'll branch on the two truth values. The left one makes it true, the right one makes it false. Now, continuing down the left branch, we've got A is true, C is true, so this is true, this is true. What about this guy? Well, this is false, and implicitly D is false because D isn't mentioned. But we want to make this guy true, so the only choice we have is to make D true. So we branch again. Okay, so there's the branch D, not D. So now what have we got? The set that we've got is A, C, D, and that's true, that's true, that's true, and this guy is true. Why? Because B is not mentioned, and so B is false. Apologies for this micro break, silly thing. B is not mentioned, so B is false, therefore this is true. So all of the clauses are true under the assignment, or the model that consists of A, C, and D. right? So we say that the model is found. Now, unfortunately, this is a typo, and I'm not able to change the slides because they're Peter's slides. This is embedded in some sort of graphic. So the set that we found is ACD, but the model is A not BCD, right? Because in interpretation, a model has to assign true or false to every atomic formula. And this thing is doing it implicitly by making B false. So we have to make that explicit, right? No big deal going on here, right? It's just we're verbalizing or making explicit the idea that anything that's not mentioned in this is false. So there's no inconsistency here. Okay, now what we've done here is we found something, an assignment of the truth variables, which makes all the clauses true. But if we look at this guy, what we'll find is that this thing actually makes one of the clauses false, and it's irrecoverable. So we make A true, that's fine. We make C true, that's fine. Now, that's false, that's false. Now, if we go and make D false, then we're down here, and there's no way that we can make this guy true. So this thing is just closed off. There's no point exploring any further, because there's no way of recovering from the fact that this guy is false. Similarly here, if we make A true, then this is true. If we make C false and A true, then this is false. And there's no way of recovering it. So there's no point exploring this branch. Now what we would do is say, well, we've explored all of these, so we found a model. These guys are dead branches. But if we wanted to continue looking for other models, we'd go over to the other side. So we go over to the other side, and what have we got? I'm going to do this faster. So we've got not A, it makes this guy false. So what are we going to do? We're going to change the implicit not B that's in here to an explicit B. Then what will we find? Well, this is true. Then this is now false because not A is true. C or A is true because not A is true. Then this guy is true because we've got not A. And this guy is false. Sorry, this guy is true. Why is it true? Because there's an implicit not D in here, right? So this is true. So what we've done is we've found that this branch leads to something which makes all of the clauses true. Now again, there's a typo here. Peter's written model B found, but really the model that we found is not A, B, not D. Why? Because this thing contains an implicit not A, so we're going to make it explicit, and this thing contains an implicit not D, so we're going to make that explicit. All right? Now this is a proper interpretation because it makes every formula A, B, or D true or false. Now C is actually left out here, but what you should be able to see out of this is that the truth value of C is irrelevant, right? So we don't want to put C to false here, right? What it's saying is that the truth value of C actually doesn't matter. I'm just going to see if I can kill this silly thing because it's getting a bit annoying. Let's see if we can. How do I kill this? How about that? All right. So let's go back to view, presentation. Right, so the point was that we don't need to worry about the truth value of C because look, this makes that true, this makes that true, this makes that true, so the value of C is irrelevant, and this makes that true, so the truth value of C is irrelevant. That's why I'm not putting C in there, because it doesn't matter whether C is true or false. Okay, so here is the official dpll algorithm. Here's the pseudocode. So what does it consist of? It consists of a function with a main while loop followed by an if, and then an if-then, and there's a recursive call. Okay, so it's a recursive algorithm, and there are some base cases, because if n is equal to empty, then you just return. If bottom is in n, then you return. Otherwise, you do something. Right? So the whole idea is that it's a recursive algorithm. Then there's a subroutine called simplify. Let's just have a look at that. It's called here and it's called here. What does simplify do? It says, if you give me a clause set and you give me a literal, then first of all, remove all clauses from N that contain L. So what's the intuition? The intuition is that I'm going to make L true. I'm going to decide that the literal L is true. Therefore, I can remove all of the clauses from N that contain L because they're going to be of the form something or something or something or something or true. And anything or true is just true. So they all disappear. Then the clauses that contain the complement of L, I'm going to remove the complement of L from them. Why? Because they're going to be of the form something or something or something or false. Because by making L true, I'm going to make the complement false. And something or false is that something. So I'm just going to delete the false. All right, so that's a simplification process. Then what am I going to do? Coming back here, I'm going to say, as long as N contains a unit clause, simplify it with that unit clause. So keep iterating using the information that's in the unit clauses. What's the information in the unit clauses? It's that L has to be true, right? So going back here, imagine we've got a set of clauses. If one of these is a unit clause, so suppose we had just, I don't know, E by itself in here, right? Then you know that because this is a conjunction, the E by itself has to be true. There's no choice. There's a choice in here because you don't know which of these you want to make true. But a unit clause means that there's no choice. So that's the reasoning here. As long as N contains a unit clause, simplify N with L and keep doing it until there are no unit clauses. Now what you have? Well, what you might have is you might have simplified everything so it has the empty set of clauses. Well, the empty set of clauses is going to be true because by removing everything that's true, you've got to the empty clause, the empty clause set, and therefore everything in it is true. On the other hand, if you find bottom in there, then you know that the unit clause, which is bottom, cannot possibly be made true. By definition, every interpretation has to make bottom to false. So there's no way that this clause set is going to be true. So you put it to false. Otherwise, from N, you choose a literal, any literal you like. A good one might be the one that occurs the most number of times. And this is this decision point that we're talking about, right? Here, we're going to choose a literal, and we're going to split on either A is true or not A is true. So L is a literal. So if we make L true, we're going to go down on one of those branches, either the left branch or the right branch. We don't know which one because it depends on the form of L, right? So what are we going to do? We're going to first of all call simplify N with L. In other words, see what happens if I were to make L true. That's this subroutine here. And hopefully I'm going to get a smaller set of clauses. And then I'm going to call dpll recursively. So in other words, start this whole process again on the result of simplifying N with L. Okay? Now, if that thing returns true, then return true. Otherwise it returns false. Then simplify. So in other words, what we've done is we've gone down this branch and we've found that it's a dead end. It returns false, right? So what we've got to do is flip it over. So what do? We flip our last decision. Our last decision was L. So what we do is we flip to simplifying N, the given N that we had here, right? Remember the N that we've got up our sleeve. We simplify it with the complement of L. So that's the analog of switching from here to there. And we call dpll. So we do the whole procedure again. Okay, let's look at some examples. So here is a set. So let's have a look at what simplify does. Here's our clause set, right? So it's a set, which is, so this is the set separator, the comma is a set separator, and everything inside it is a clause. In other words, it's a disjunction of literals. Disjunction of literals, disjunction of literals. Now the L that we're looking at is this guy. Okay, it happens to be a positive atom, A, And what are we going to do? We're going to run this procedure, right? So what does it say? It says remove all clauses from N that contain L. So what do? Here's the L. Are we going to remove that one? No. Are we going to remove that one? No, because it contains not L, right? Are we going to remove that one? No, because it contains not L. Are we going to remove that one? Yes, because it contains A exactly. So here we are, right? So this whole clause is gone. Then what are we going to do? Then what we're going to do is we're going to delete the complement from all the remaining clauses. So we're doing it in 2 steps. So this guy's going to be left alone because it doesn't contain the complement of A. This guy contains the complement of A, and this guy contains the complement of A. So what's going to happen? These are going to disappear, leaving C. This is going to disappear, leaving D or C, and this guy's going to be left alone. So there he is there. Okay, now what? Now we're going to simplify this clause set by C. So for example, imagine that we decide that we're now going to choose, right, we're going to choose a literal, and what are we going to choose? We're going to choose C. So what's going to happen? We're going to delete any clause that contains C, so that guy's going to disappear, and we're going to delete not C from every clause. So that's going to disappear, and this guy's going to be left alone. So here we are. C clause disappears, right? So that guy disappeared here, that guy disappeared here, right? And the not C is going to disappear. Okay, what now? Now we've got this, and we've got to make another decision literal. So we're back here, and what are we going to choose? Let's suppose we chose D. So D is the literal that we're going to simplify with. So what will happen? This guy will disappear completely, and this guy will disappear, leaving not B. Okay. So that is the basic dpll procedure, and you keep on going, and it's guaranteed to terminate. Why is it guaranteed to terminate? Because if you look here, right, every time you go deeper, you're making another decision, and our clause set is going to contain only a finite number of literals, right? So going down here, you can't create an infinite branch, because sooner or later you will have made a decision for every literal that appears in the clause set. And then you've got to have a decision. Either they're all going to be true, or one of them is going to be false, depending on what your evaluation was, right? So every branch is going to terminate. Then when you get a new branch, well, you get a new branch when you flip from one decision to its negation, or its complement, right? But again, if there are a finite number of literals in your clause set, then there are only a finite number of flips that you can make. So any tree for any finite set of clauses is going to be finite. And so you're going to be able to decide at the bottom whether there is a branch that makes all of the clauses true or not. Okay. Now, the front line in dpll is making it faster, right? So this basic procedure that we've seen is actually not all that fast. But there are a whole bunch of optimizations that researchers have found, which makes it a lot faster. And here are a couple. I'm going to mention what they are, and I'm only going to cover the first one, lemma learning. All right? I'm not going to worry about the others, but they exist. So, what does lemma learning say? It says add new clauses to the clause set as branches get closed. I'll give an example in a moment. Right? So the idea is that when down here you find that a branch is closed, right, then you learn something and you restart from the top again, right? So that's why it's called learning. So you learn something, the fact that one branch failed. So what's the goal? The goal is to reuse information that is obtained in one branch for subsequent derivation steps, right? So don't make the same mistake twice. Backtracking is another optimization, and the idea is that up here, so what we did here is when we got down to the bottom here, we backtracked and we flipped the truth value of the D, right? And then when we got up here, we we flip the truth value of C. And then when we go here, we'll flip the truth value of not A. Now, under certain conditions, what you can tell is from down here, what you can tell is whether or not it's worth flipping D or not, right? And the idea is that if you can tell that from down here it's not worth flipping C, well, don't flip C. You already know somehow that this branch is going to close, and so you go up there and you flip to the other side. All right? So that's called back jumping. Randomized restarts. So the idea is that we made some decisions, right? And we're down here, we're somewhere in the middle of this tree, and for some reason you feel that you're not making any progress. There are some heuristics to judge, right? For example, the number of clauses that are being satisfied has stayed the same for some number of attempts here, right? You're going deeper and deeper, but you're not really getting anywhere. You're not getting further. And so what you do is you just say, I'm just going to give up on this search space and just go right up to the top. And instead of choosing A and not A, I'm going to choose some other completely different literal, right? So the idea is that you must be random. You don't do the same thing again. You somehow do something totally different. There are also variable selection heuristics. So for example, at this point here, right, we have a choice. Now if you can choose the literal carefully, maybe you'll close the branches better or faster. So for example, as I said, one heuristic is choose the literal that occurs in the most number of clauses, right? Because what you're hoping to do is get an answer quickly for all of those clauses, right? Because by choosing it, all of those clauses that contain the literal are going to be deleted, so you're going to reduce the number of clauses by a lot, and all of the clauses that contain its negation are going to have the negation deleted, so they're going to get smaller, right? So you're going to delete a lot of clauses, and you're going to make a lot of clauses smaller. Well, hopefully, that'll mean you'll get a unit clause, and as soon as you get a unit clause, you've won, right? So that's another heuristic. And the final heuristic is something called two-watch literal technique. I'm not going to go into that because it's just a little bit more complicated than you need to know. Okay? All right. So what I'm going to do in the rest of the lecture is look at this lemon learning. So let's go back to our example. So we have a set of clauses, right? And what we've done is we've used the dpll procedure and we've decided to split on the literal A, right? Because this clause was false, and so we're going to decide on A. That's the one that makes it true. This is the one that makes it false. So then what? Then what we find is that, well, if A is now a decision literal, then we delete not A from this guy, right? So we get B. So B is now a unit clause, and so we're going to write B down here. Right? So what's going on is that we decided A, and then we simplified the procedure, we simplified the clauses by the fact that we had made A true. Well, if A is true, how do we simplify the clauses? We delete every clause that contains A, there isn't one, and we delete not A from every clause. It's only this guy. So we've deleted not A from here, leaving B. Well, B is a unit literal, right? B is a unit clause, so we have no choice. We're going to put B down here. Now what? So this guy is happy. This guy is still false. So now we're going to split on C. So what do? The left branch says make C true. The right branch says make C false. Then if we go down the left branch, how do we simplify with this unit clause? Well, we delete every clause that contains C. There isn't one. We go back to every clause that contains not C and just delete the not C. Right? So this is going to become shorter, not D or not B, and this is going to become D. Well, then D is our decision because we're forced to make D, right? So now we're down to here. Okay. Now what? Now let's see. This is true. This is true by D, and this is the only clause that isn't true. Let's see. Is there any choice? Well, this is false, and this is false. So what we've got is we've actually got a closed branch here, because there's no way that we can make this clause true. So conflict. Clause 3 is now false. There's nothing we can do. We can't change the truth value of anything. Clause 3 is now false. So what have we learned? What we've learned is that deciding on A immediately forced us to make B true because of this clause. Then deciding on C immediately forced us to make D true by this clause. And somehow these decisions are not giving us a model for the third guy. So these decision points are somehow wrong. Now, what are the things that we've actually decided? The things we've decided is to make A true and to make C true. The other guys just came by unit propagation. So what we've learned is that A and C is somehow bad, right? Making A true and then making C true is somehow bad. So what do we learn? We learn, well, don't do it. Avoid one of the decision literals. So you either have to avoid A or you have to avoid C, right? In other words, make A and C false. How do you make A and C false? Well, not A or not C. You make one of them false or both of them false. So what we've learned out of this is that embedded in here is the information that A and C is a bad interpretation because there's no way that it'll make this guy true. So avoid the interpretation that makes A true and C true. In other words, every interpretation always has to have one of them false. So what we'll do now is we'll go all the way back up to the top and we'll restart with a fourth clause, which is the one that we've learned, not A or not C. All right, so here we are. Ignore all of this because this is to do with resolution. Here we are. So we start again and we decide on A. So we go down the left branch. Now A is a unit clause, and remember we've got a clause number 4, which is not C or not A. Well, what does it say to do with unit clauses? It says delete all occurrences, all clauses that contain A. There isn't one. This one doesn't contain A, so we don't delete it. But now it also says delete not A from all the clauses. So we're going to delete not A from here and get not C, and we're going to delete not A from here and get B. But if we just give priority to the learn clauses, then what we immediately get here is that the not A gets deleted and we get not C, right? So what we've done is, look, we've effectively gone down there and moved the decision point not C up higher, right? So now, of course, to continue, we may have to make a decision point on B, or we may have to make a decision point on D, but we're never going to make this mistake again, right? Because having made part of the mistake, we avoid the second part of the mistake. That's what this guy says, right? It says either avoid A, or avoid B, or avoid both. So having not avoided A, we have to avoid the C. And so we've restarted, but what we've done is we've learned something from our previous mistake. So what lemma learning does is it makes your clause set bigger. By every closed branch allows you to add a learned clause to the set. And so what you're doing is you're reclaiming all the memory that you used in this search, right? And immediately recreating that branch. Now you're having to do some more work by recreating that branch, but in general, what you find is that this speeds up the procedure a lot. Okay? Why am I saying to ignore this? Because this is going to be the topic of our resolution lecture, and what it's showing is that the clause not C or not A is actually derivable from the three clauses that we've got, right? So it's just showing that lemma learning is something that's derivable. But we'll talk about that in the next lecture. Okay, so in this lecture I've only taken about half an hour. So I mean, I don't think I've gone particularly slowly or anything like that. So let's just go over it. What did we do? What we did is we wanted to do dpll. So first of all, what we did is we figured out a way to put things into conjunctive normal form. So what is it? It's a matrix where every row is a disjunction of literals and the rows are conjoined together. So every row is a disjunction of literals and the rows are conjoined together. How do we put things into CNF? You first put the formula F into NNF, and then you look at every occurrence which breaks this CNF condition and rewrite it using this logical equivalence, meaning that you're not changing the validity of the formula, right? So this is bad because we've got an OR outside of conjunction, and what we're demanding is we're demanding the conjunction to be outside the ORs. So we flip this over to here, and now the ORs are inside the conjunction. Similarly, if the disjunction is on the left-hand side, we push it inside, and the conjunction is now on the outside, and the disjunctions are inside. This procedure will terminate because our given formula is a finite size, and at most this is just making a little bit bigger, right? It's not making it infinitely bigger, it's making it a bit bigger, and so now the bad guys are one level of nesting downwards. So this is guaranteed to terminate. Okay, now what does Davis, Putnam, Longman, and Loveman do? It works on clause sets. So what's a clause set? Well, a clause is a disjunction of literals, so it's one of these rows, right? A clause is one of these rows, and a unit clause is something which consists of just one literal. So up here, it's a row that consists of just one atom or just one negated atom. So that's a unit clause. And the convention is that if I give you a CNF formula, then you're going to write it as a set where you only keep all the disjuncts and get rid of the conjuncts, right? And what we want to do is what we're looking for is an assignment that makes this guy true and this guy true and this guy true and this guy true. So we want to make every member of the clause set true. That's what the dpll algorithm is trying to do. And why is that? Well, what it's doing is, if we want to know whether this formula is valid, then what we want to do, or one way that we can do it, is to say that the conjunction of this guy plus the negation of this guy is unsatisfiable. So what we'll do is we'll convert this into a clause set and see whether there is a satisfying assignment. If we find a satisfying assignment, then we know that this is false, because there's a way to make these guys true and make this guy false. If there is no way that we can make this false, then it means that whatever assignment you give, if it makes these guys true, it's got to make these guys true. So that's the way we'll decide an implication of that form. What did we do? Then what we did is we worked with trees where we looked at decision points, and the branches had to be consistent. So the branches contained nodes. Every node contained a literal, and the branch is consistent, meaning that there are no two nodes such that there's A in one and not A in the other, right? Then we interpret these branches as interpretations. The idea was if A was in the branch, then A was going to be true. If not A is in the branch, then A is going to be false. And if A is not mentioned in the branch at all, then it was going to be false. So then what did we do? We looked at a way that we could decide on certain literals. So the empty assignment makes everything false. Then we made this guy true by deciding on A. Then we made this guy true by deciding on C. Then we made this guy true by deciding on D. And this guy came along for the ride because implicitly there's a not B in here which makes that true. Then there's a typo on this slide. The model that we can extract from this is actually this guy, because we have to give an interpretation to the formula B. It's actually essential. It has to be false, right? Because it's the only way that we can make this clause true. B has to be false. Okay, then we flip to the other side, and what we found is that not A and B made all of them true. Why is this guy making this guy true? Because there's an implicit not D in here. There's a typo in here. Because what we found is that not A and B are essential, but not D is also essential. We have to make it explicit rather than implicit in order to make this guy true. Why haven't I put C in here? Because actually the truth value of C is irrelevant, right? Because this thing, the B makes that true, the not A makes that true, the not A makes that true, and the not B makes that true. So the truth value of C is actually irrelevant. I don't want to put C or not C in here because the model doesn't care. Okay, then I gave you an algorithm and showed you how it works. To simplify with a literal, you delete all the clauses that contain it and shorten all the clauses that contain its negation. To do with another one, you delete all the clauses that contain it and shorten all the clauses that contain its negation. To simplify with D, we delete the all the clauses that contain it, and we shorten the clauses that contain its complement. And all we're left with is this. Then I talked about a couple of optimizations. The only one that I really went over was lemma learning, and here's the example. So we decide on A and not A, so we go down here. Simplifying with A means that we delete that guy, so we've just got a B. So we're forced to make B true. Then we split on C. Then unit propagation on C means that we delete this, which means we're forced to make D true. We're down here. And now what we find is that this is false, and this is false. So this clause is false. There's no way that this branch is going to make all of the clauses true, because this guy's just, all of them are false. So what do? We look at our decision neutrals, which were A and C. B and D came by unit propagation, so they were a consequence of the decision. They're not decision neutrals. And what we've learned is that we have to avoid the conjunction A and C. So what we do is we insist that one of them is false, and we add that as a new clause. Now, if you do this, when you do lemma learning and just negate all the decision neutrals, you will always get a clause. Why? Because each one of these is a literal, right? And negating it is going to give you a clause, right? You might have to do a double negation elimination somewhere, but you'll always get a clause. So you add 4. Now we restart. What do? We decide on A, and then we've got a unit clause that says not C or not A. So what does simplification say? It says delete the not A, giving you the not C immediately. We'll also get a B from here, but that's going to be down here. Right? So the idea is that by lemma learning, we've suddenly jumped over here, and we've got an A and a not C, and we're going to get a B immediately down here by unit propagation. So we will get the B, it's just that we've completely avoided redoing this because it was a mistake. Okay, now as I said, this is a research area, so these things are implemented and very efficient sat solvers that you can find on the web. There's a very fundamental article which appeared in the most prestigious journal we have in computer science. This is called the Journal of the Association for Computer Machinery. It was in 2006. And basically what you're seeing here is that over the last 20 years, automated reasoning techniques have conquered classical propositional logic, right? These sat solvers can now handle clauses that contain hundreds of atomic formulae. Now remember, a clause or a formula that contains 100 atomic formulae has 2 to the 100 possible assignments to it, right? There are 2 to the possible assignments that you would have to check in order to make sure that it was valid. So what we're able to do is easily handle formulae with 2 to the 100 variables. We're talking in tens of seconds, right? Now 2 to the 100, I think, is more than the number of atoms in the known universe, or something like that. So what you're seeing here is that over the last 20 years, from about 2000 onwards, automated reasoning community, the research area that Peter works in, has essentially conquered the satisfiability problem for propositional logic. Okay, I'm going to put this up now and get ready for our next lecture. So, where's our recording? Pause the recording.